Hey everyone, so I wanted to make a quick video talking about the stability theorem because I know that's a little bit trickier to find on YouTube since it has to do with discrete time dynamical systems. So anyway, here we have a setup where on black on the solid curve is a updating function, and the dashed red curve is like the line y equals x, but really remember it's x sub t plus 1 equals x sub t. It's the equilibrium line. So we have this point of intersection right here. And if we had to cobweb this, well, you sort of pick a point just a little bit to the left and just a little bit to the right. And the algorithm is you move vertically to the black line and then horizontally to the red line and just repeat. So let's go ahead and have it do it for us. So there we go. All right, and we can see that the cobweb, we begin on this vertical black segment on the right. We go vertically to the updating function, which is the black line, horizontally to the line y equals x, which is the red dashed line, and then vertically to black, horizontal to red, and so on and so on and so on. And you can see we're marching away. Okay, so it looks like this equilibrium point here is unstable, all right? And if you just understand how lines intersect and whether you're stable or unstable, you will understand the equilibrium or the stability theorem, because really that black function was not a line at all. It was a parabola. Oops, let me go home again and see if I can get a better zoom in. Zoom in. There we go. Right? And so when we begin at a spot that's a little bit to the left of the equilibrium, well, when we say a little bit to the left, we mean like you can really just imagine these are two lines because you want to zoom in to where it looks like a line, and that tells you the behavior. And so the reason we are moving away from the equilibrium point is because the slope of this black line is bigger than 1. So let's pop over here so we can doodle a little bit and talk about why that's the case. All right. So if I am going to graph an updating function, so maybe I have an x sub t and an x sub t plus 1, then I need a reference line for this is my equilibrium line. I'm going to call it y equals x, but that's an abusive notation. Technically, it's called x sub t plus 1 equals x sub t. This is my equilibrium line. It's when your input equals your output. There's no change. Okay, so now I want to graph an updating function that has a slope bigger than 1. Well, since the red line has a slope 1, to be bigger than it means I have to be steeper than the red line. So let's go ahead and do that. Boom. All right. And now, if I were to cobweb, I begin somewhere, x0, I go up, and I hit my updating function. And once I hit it, the y-coordinate tells me my next iteration, so in this case, x1. But I want my y-coordinate to become my x-coordinate, and that's why we travel over to the line y equals x, because now my y-coordinate becomes my x-coordinate, and so this point would be x1, x1, because my y-coordinate here becomes my x-coordinate, but also it's the same as my y. It's the line y equals x, so they're the same. And then I go down here, boom, and so now vertical travel means I kept the x-coordinate fixed, so it's x2, but now since I'm on my updating function, your updating function, the y value is your x sub t plus 1, and the way you got that was by plugging x sub t into your function. So if I plug in x1, my output is x2, right? And that's what this is saying here. So anyway, and then I come over here and so on and so on. All right, now I traveled away because the slope of the black line was steeper than the slope of the red line. In fact, it's because the slope of the black line was bigger than 1. So it's not just that it was steeper than the red line, it's that it was bigger than 1, the slope of the red line is 1. And if we were to cobweb, so you can imagine coming up, okay, hit here, hit here, hit here, I'm also traveling away from my my equilibrium point. So that's slope bigger than 1. Let's check. There's also something that happens with slope less than negative 1. So now I need a reference for a negative 1 slope. So I sort of I'm trying to get a right angle here. That way the slope of this line, I'll just call it m because slope is a lot of writing, is negative 1. Okay. And so now I'm going to show you that if my slope is less than negative 1, so here's a number line, here's negative 1, my slope lies over here somewhere, right? It's to the left of negative 1, here's 0 and stuff like that. Then I'm still unstable. So the way I get steeper than negative 1, well, this is negative 1. To be steeper, okay, I have to be steeper. So I'm going to come on through here like this. And now if I cobweb, Okay, let's do it. So I travel vertically to my updating function, horizontally to y equals x. Vertically to updating function, horizontally to y equals x. Vertically to updating function. And so you can see I'm moving away from equilibrium. Oops. I just do it in a spirally nature. And in general, negative slope of an updating function tells you that you spiral. Okay? Play around with that. Draw a few different, just give yourself a little setup. Draw a negative slope updating function. See that you spiral every time. Okay? Anyway, so what these two scenarios have in common is that the equilibrium point, so the equilibrium point is unstable. And the slope of my updating function is, well, let's do this. So the slope in absolute value is bigger than 1. So here's my number line, here's positive 1, here's negative 1. My slope lies in this region over here. I'm either bigger than positive 1 or less than negative 1. Okay, that's the unstable scenario. And truly, you only have to understand what goes on with lines, because if we pop away from lines and we look at different functions, so that's right, in order for this to work, I need to kill that. I need to relabel you as f of x. Okay, so now I have this blue curve here. And, all right, so it's not a line, it's a parabola, but if I zoom in to this equilibrium point, we can fool our eyes into thinking this is a line. And what's a good spot to start at based on these little things? Let's see. Let's start at. Let's get this to go away. We'll do like a 0.625. That looks like it might be a decent 5. There we go. So now you can see where we begin. This black line on the right is telling us that we began x0 equals 0.625. We hit our updating function, and we start spiraling toward the equilibrium. Now, why we spiral toward the equilibrium? Well, in this case, that's because the slope of the blue line is less than 1. All right. If I want to make it bigger than 1, let's go ahead and just... Oh, that's going to change the equilibrium. Sorry. Yeah, this should work. Oops. Oh, man. All right, I'll just make it really dramatic. Let's go to like a 7. And, all right. Let's zoom in. And it's really chaotic, but you can see, like... So I start at these spots here where I'm moving around, and it's just crazy chaotic. I'm not really heading towards the equilibrium. I'm sort of just going everywhere, okay? But I am spiraling. We can see we're spiraling type of structures. It's very weird. And that's because in this case, the slope of the blue line is bigger than 1. And we can kind of see that by just sort of eyeballing it, but we can get more specific here. So if you notice, a is 4, and the equation I'm looking at is ax times 1 minus x. So let's hop over to the other page and do a little math, little trickery here. Okay, so ax 1 minus x. This was our updating function, which is the same as ax minus ax squared. All right, and so here's my updating function. Let's go ahead and take its derivative. So in this form, it's easier to take a derivative of, so a minus 2ax. And if you were to find that equilibrium point, well, actually here, we'll just have Desmos tell it to us. So if I tap on here and tap that point, so 3/4. 3/4 is the equilibrium point we were interested in. So in our case, a was 4, so this would be 4 minus 8x, and the equilibrium point of interest was 3/4. Okay. Well, so f prime of x is going to tell you the slope at x. And we care about the slope at the equilibrium point, so we care about f prime at 3/4. So this is 4 minus 8 times 3/4. That's 4 minus, and the 8 and the 4 cancel, you get a 2, and that becomes a 6. And so you have negative 2. So it turns out, if I hop back over to Desmos, let me just graph the tangent line really quick. So y minus, and the y value equals the slope, x minus the x value. Okay, and let's make that a different color just so it sort of shows up a little differently. There we go. So there, I've graphed the tangent line to the updating function, and the point is that when I zoom in, you cannot tell the difference between the updating function in blue and the tangent line in green. I made sure you can see a little bit toward the bottom, but if I just keep on zooming in, eventually it'll work. And so locally, all you have to do is understand the intersection of lines to understand the stability theorem. Okay, so let's go ahead and write down the stability theorem. So what it says is, if you have some kind of updating function, so x sub t equals x sub t plus 1. So we have some updating function, and it's differentiable, and we're going to have some kind of equilibrium point. So equilibrium point, oops, how did I do that? Here. We'll call this x star, because that's what the book calls it. So x star is a point that satisfies, so what does equilibrium point mean? It means x star is equal to f of x star. If you want to see that above, if you plug in, so let me write down what f of x was in this case. Remember, a was 4, so it's 4x minus 4x squared. If you plug in 3/4 to x, you're going to get that as an output as well. So let's just try it really quick. So 4 times 3/4 minus 4 times 3/4 squared. So these 4's cancel. You get a 3 minus. This 4 will cancel one of these, but there's still actually 4 down there. So we'll end up getting a 9/4. And we need to get a common denominator, so I'm going to do times 4/4. So that's a 12 minus a 9/4. That's 3/4. So what we put in is what we got out, right? And that's what this is saying. What you put in is what you get out. That's what an equilibrium point is. Okay, so we have an updating function. We have an equilibrium point. So now if we were to take the derivative of the updating function, so then x star is stable if the derivative of the updating function, and then you check at x star. So what is this telling you? This is telling you the slope at x star. Okay, that's what this object is. In absolute value is less than 1. So if the slope at x star is less than 1 in absolute value, so what does that mean? Let's draw a quick little picture here. So we have this. This is like our y equals x. This is just a reference. Let's put down another reference, because this has slope 1. Let's put down a reference with slope -1. So I kind of want to shoot for a perpendicular intersection here. Okay. So according to this sketch, the equilibrium point is right here. Okay. Now, my updating function needs to have a slope less than 1 in absolute value. If you think about it for a while, you can start to realize that means you have to go from this region here to this region here. Okay, let's talk about why that is. So first off, if I do go from yellow to yellow, now I claim my slope has to be less than 1 in absolute value, because you can sort of imagine if I start twisting the line I'm drawing, the most I could twist it is when I hit the boundary. This boundary has a slope of +1. So maybe like here's a slope of 1/2. Here's a slope of 0. Here's a slope of -1/2. Here's a slope of -1. I'm sort of stuck in this region where, let's rewrite this inequality, -1 less than f prime of x star less than 1. Okay, so my slope is between -1 and 1. That's exactly what that highlighted region is doing, my little bow tie region. That's the stable region. Okay, this is stable. Writing. Okay, going from like here to here. Now, all right, so that's one scenario. X star is unstable when, or let's just say if, the slope in absolute value is bigger than 1. All right, and it turns out that means you go from this region here to this region here, or vice versa. Okay, so if I have a very steep positive slope, like a slope of 2, well, let's think for a second. This line here is a slope of 1. So I have to be twice as steep, and I want to go through my equilibrium point. So maybe it's something like this. Okay, I'm going purple to purple. And in fact, if I was just a little bit bigger than 1, then I want to be pretty dang close to that dashed red line, but I'm still a little bit bigger than 1. That's still purple to purple. Meanwhile, this line has a slope of -1. So if I make -2, I should be like twice as steep. Boom. And so if you think about it, you can kind of realize that going between these purple regions means your slope is bigger than 1 in absolute value, which, okay, let's also rewrite this the same way we rewrote before. So this means f prime at your equilibrium point is less than -1, which is sort of like, okay, so here's -1, here's 0, here's 1, it's over here, or f prime of x star is bigger than +1, it's over here. Okay. So this is what the stability theorem says. It says if your slope is near 0, meaning less than 1 in absolute value, you're stable. If it's bigger than 1 in absolute value, you're unstable. But there's a number that we miss, right? And that is if your slope right on, dead on equals 1 or -1, so we'll say plus or minus 1, this is inconclusive. You would have to continue to cobweb and see what happens, okay? So let's see. Let me do an example where that could be stable and where it could be unstable. So I could have, okay, there's my y equals x line, and just for reference, let's go ahead and give ourselves a -1 slope. So if I kind of come in here and I start to look more and more like the red line, and then I go away like this, okay, if this is my updating function, x and t, then I tried to match the slope of the red line y equals x right at that equilibrium point. So in other words, what I'm trying to do is I'm trying to make it so that way f prime at this equilibrium point here is 1. I tried to match slopes. And yet, if we were to cobweb, we would find that this spot here is stable. And the reason is actually because like all the slopes leading up to the equilibrium point, all these slopes are less than 1. Similarly, all the slopes leading away from the equilibrium point are less than 1. And so that'll actually do the job for us. We will become attracted towards the equilibrium point. Whether we start there or start here. Oops. Boom, 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 boom. So this is a case where even though my derivative is 1, I'm stable. But that's not always the case. I can play the same matching game. Okay, I can play the same matching game, but now I just want to stay in different regions. So sorry, let me just... So up here, I tried to stay in the stable region right up until I hit the point of equilibrium, and then I went back into the stable region, right? And as a result, my equilibrium point is stable if I check cobwebbing. But it's not enough to check the stability theorem because, you know, my slope is 1, so it doesn't apply. So I'm going to do a similar trick, but I'm just going to go from the unstable region to the unstable region. So let's do it. So what I want to do is I just, at the intersection, I want to look like this line, but I want to be in the unstable region, so I can do that. And then look like the line, but be in the unstable region, so I can do that. Okay, if I cobweb this type of updating function, then my point will be unstable. And we can check, so I come up here and I hit the updating function, I go to line y equals x. Updating function, y equals x. Updating function, I mean, you can see I'm traveling away, right? Let's check one more. So I just want to show you what happens if we mix and match, right? So I could go to, say, this unstable region from this stable region. And I'm going to do it in a way to have slope 1, so I need to look like that tick mark. So I can come in here, look like the tick mark, and come out this way, right? And now if I cobweb on the left, updating function, y equals x. Updating function, y equals x. I'm traveling towards the equilibrium point. It looks stable from the left. But if I check on the right, updating function, y equals x. Oh man, unstable on the right. Okay, and what all of these three examples have in common is at the equilibrium point, I have a slope of 1. That's by design. So for all of these functions, f prime at x star equals 1. All right, and in some cases we're stable, in some cases we're unstable, and in some cases we are mixed. All right, so stability theorem. You have an updating function. You have an equilibrium point. You want to know, is my equilibrium point stable or is it unstable? Well, you take the derivative of your updating function and you plug in your equilibrium point. And that's going to give you objects like these. and you just ask yourself, which category does it fall into? In absolute value, is it less than 1? In absolute value, is it bigger than 1? Or am I equal to 1? If you're equal to 1, you're inconclusive. If you're bigger than 1, you are unstable. And if you're less than 1, you're stable. And why this works is because if we just, let me get rid of these iterations here. Oh, that's not, there we go. Is despite having a nonlinear curve, so in blue, I'm not linear, stability is really a local property. And I want to know, if I start out near my equilibrium point, will I travel towards my equilibrium point? And so if I zoom in, then locally, these things just look like lines. And so all we care about are the slopes of intersection. I did have one more function to put up, not that it really matters, but just to show that, like, you know, you can have functions that seem really gross. Like arctangent is a function I don't want to mess with most of the time. But, you know, okay, so I do have an equilibrium right there, 2.132, whatever that is. It's probably something involving like irrationals and pi and stuff. But if I zoom in, then we can see, oh, wait a second, it looks like lines. And in fact, my green line looks like it's going from the stable region to the stable region, right? If I kind of imagine, in fact, here, let me just do the, let's play with this a little bit. So I want a line that goes through the points 2.1323, comma 2.1323. So let's make a line that does that. So I use the point slope formula, 2.1323, is that it? I wish this would just stay up, yeah. And 2.1323. And I want to have a slope of -1. So let's make a slope of -1, and then pop, there it is. Okay, and let's know that this is a reference line, so I'll use my typical notation for reference line, which is dashed red. So now we can see the green curve is going from the stable region to the stable region. It's going to be stable. And if you were to take the derivative of arctangent, which is really gross and it involves the inverse function derivative rules, and you were to plug in x equals 2.1323, you would get something less than 1, right? And we can see that in this picture. So, okay, that's it for this video. I just want to talk about the stability theorem and give you these visuals here with the stable region and sort of like designing functions that are stable or unstable or mixed stability using this region approach. All right, see you next time.